Hi everyone, and welcome back to this series of videos which is about text analysis with a focus in the financial domain. In the first video, we have been taking a look at how you can pre-process text. And today we're going to continue with the process, what you are doing after you pre-process the text data. Maybe let me start with a few general things about that. Okay, so what in most of the cases is done is that text is transformed from its raw input into some numerical form. Okay, that means if you have what in general we call a document can be a sentence or a page or an article. This is a very rather general description of a text. It's going to be transformed into what we call a numerical representation. And that just means in the beginning you have text, and after you did something, this text is represented by numbers. Okay, because usually the applications, the tasks that are there, are then handled by different algorithms. Can be algorithms from the machine learning domain or something else, and those algorithms usually only work with numerical input. Okay, so this is why I would say in almost all the cases it is always about transforming raw text into a meaningful numerical representation. And today we're going to start with a, I would say, rather simple way to transform your text into a numerical representation, which is somehow related to counting word frequencies. But as we will see as the videos continue, this is also going to be done in more sophisticated ways, always with the aim to have an even better, a more characteristic numerical representation of the original text input. All right. So let's take a look at this concrete example here that I used to start, or like that I would like to start as a start for a demonstration. So this is related to what is in general called a supervised learning task. That means we have a certain target variable, a variable of interest. In that case, it is the sentiment of sentences. Okay, and sentiments here in that example is annotated. Rather, a sentence can be positive, can be neutral, or can be negative. So again, as always, this, or as I'm always trying, this notebook is the link to it can be found in the video description. And here, once you need to have a proper Python environment running, and also I think you need to install, for instance, the datasets package. But if you would execute this, what we are taking a look at here is a dataset that is called Financial Phrase Bank. It is quite, I would say, popular, and it includes sentences, as far as I'm aware, from news about stock market listed companies. And there are different versions of the dataset here. Here, if we call this as the sentences 66 agree, the sentences have been labeled by different annotators, and those are only the sentences where 66% of the annotators can agree upon a certain sentiment. Okay, and so this is how sentences look like here. Okay, so here, for instance, the first one is, according to Grant, the company has no plans to move all production to Russia, although that is where the company is growing. Okay, so financially related, this is why I'm using also this example. Here, just also as a, to give you a better idea about the sentences themselves. So overall, I think it's 4,080 or something like this sentences. And as you can see, the majority are labeled to be neutral. And then we have a little bit more positive than negative sentences. And here, we don't need to read through this in this video, but here are also some examples from the neutral, from the negative, and from the positive categories. All right. So if we have those sentences, we can pre-process them as we have been talking about in the first video. So here I'm using the simple pre-processing routine from the Gensim package, which mostly, lower cases everything. It removes the punctuation, it removes the numbers, and then, for instance, the first sentence that we have been reading through before is now looking something like this. Okay, so let me zoom in a little bit so we can see this better. So no big deal here, I would say, and especially still very readable to us as human beings. All right, then The first way, and a simple way to to bring these sentences here into a numerical representation is simply by taking a look, okay, how many different terms are appearing in those sentences here. So for this example, I am restricting myself only to the first 5 sentences because that is enough. And with this little amount of sentences, we are also able to really take a look at what is happening here. Later on, we are going to use the overall amount of sentences to do whatever we want to do here. Okay, and then counting word frequencies here to have a common understanding of the wording. So what we have here is, if we would split the sentences here, for instance, by white spaces, then we would have tokens. Okay, so I think we've been talking about this definition in the first video. So it's in general, tokens just a sequence of characters, but here, if we do this in a, would say, more human-alike way, then it would be very natural to treat the white space separated here words, and let's call them, or also instead of words we can say those are the tokens. And for instance, over those 5 sentences there are certain tokens that do appear more often. For instance, company, here's twice. So the unique word or token is then called the term, and the overall dictionary is then the number of all terms. Okay, so token can appear more than once, and the term is just how we call the unique, in our example here, word. And the dictionary is just the set, so the collection of all unique words that can be found in this dictionary here. And then what we can do for every sentence, we can count for how many times a certain term is occurring. So this is why we went up with a term frequency representation. And when you want to use with Python, you can use the count vectorizer. Okay, so let's pre-process this here. And then the count vectorizer, if you take a look in its documentation, it has several arguments that you can give to it, and which is going to influence the final numerical representation. In our case here, what I'm doing, I'm just saying, okay, please remove the stop words from a list of English stop words. And this is the minimum document frequency. So that means please only take into account terms that do appear in at least 25% of the documents. So in our case, we have 5 documents because we have 5 sentences. So in 25% of those 5 sentences, the term must be found to be used as an actual term that we're going to look at for how many times it occurs in a different sentence. Because why I'm doing this here, it's just especially to that we can still take a look into this, because if you don't set this here, you can see that even for just 5 sentences, we already end up with 59 unique terms that do occur among the 5 sentences. So that would mean, you can see this here. So this is what we would call a numerical representation of the first sentence. So the first row here. These are then the numbers that do represent this sentence here, right? But yeah, I mean, this can grow quite large. And large means high dimensions, which is often, critical, or can be at least very challenging for algorithms that may use this numerical representation later on. So sometimes it makes sense to at least have a little bit, some thresholds here that try in a reasonable way to keep the overall number of terms as little as possible. But of course, there's a certain trade-off here. The more terms you add to the dictionary, the finer or the more informative the numerical representation may be. At the same time, the higher the dimension of the representation, the more challenging it gets for algorithms that use these numerical representations later on. This is due to what is called the curse of dimensionality, which we are not going to discuss in this video here, okay? So if we set this here, then we can see, so in the Pythonic way, you can fit and transform these sentences, and then you can see what is actually meant by the numerical representation of the sentences. So for instance here, then this is the representation of the first sentence, and for instance, that would be the representation of the, here the second sentence from the end of the sentences here. All right, so this is a very fast way, and I would say this is model free, because you don't need to train this algorithm to, generate this numerical representation. However, even though, for instance, we removed stoppers here, it may be further refined, which sometimes can be helpful by weighting those terms in different ways. And the most popular way is the so-called inverse document frequency weighting. And here the reasoning is there may be some words or some tokens, or some terms, better to say, some terms that do appear in a few documents, but not in the remaining documents. And if that's the case, it is especially maybe those terms are the ones that can be really helpful in characterizing the documents and maybe in differentiating between the documents. And to give those terms a higher weighting, what is calculated is the inverse document frequency. And here I've been writing down how it is calculated for the sklearn package when you use the term frequency inverse document vectorizer, okay? And so that is here. So if we have n being the number of all documents, in our case 5, and nj is in how many documents is the term appearing, okay? So if we have a certain term that appears for 2 times, then we have here 5 divided by 2, right? So this number gets the higher this number is higher if a term is occurring less or little over the overall amount of documents here. And then using the log of something is often done, and I guess it's the same here, to kind of normalize very extreme values, because if you use the log, then very extreme values, they're getting like smaller, and so I guess this is just the reason for doing so. And then also the plus ones here, more or less, they are, let's keep it like this, they are smoothing, and also they make sure that you don't run into mathematical and or numerical problems dividing by 0 or something like this, okay? And yeah, this is an argument that you can pass to this term frequency inverse document vectorizer. This, if you set smooth IDF to false, it is being calculated like this. And if you set it to true, which I think is the default setting, then the inverse document frequencies, they are calculated like this. Okay, so if we do this here, and now for a moment, please be aware that I'm setting here another argument, which is called norm to none. We're going to come later to this. You can see what's happening here. Okay, so for instance, if we compare that, we have been seeing according is here equal to 1. And now using the term frequency inverse document vectorizer, it is 1.9 something, right? And as this is called the term frequency inverse document frequency matrix, what is done to calculate those numbers here, the term frequencies, so these ones, they are multiplied by the inverse document frequencies. Okay, so, and this is, derived internally. So once you call the fit or the fit transform method to the term frequency inverse document vectorizer, then later on, if you want to, you can get the inverse document frequencies, or you can take a look at them by calling this attribute here. Okay, so if we execute this here in that way, then we can see this. And if you would like to see directly to which features those are the inverse document frequencies, I think there's also a function which is called something like get feature names out. Okay, but this is just the ordering that you can see also if you take a look at this matrix here. So according has an inverse document frequency of 1.9. So this is why here we can see, okay, 1 multiplied by 1.9 something. This is how we end up here with that number. Okay, so for instance, then company has an inverse document frequency of 1.5 something. It is occurring for 2 times in the first document. This is why we have 2 times 1.5 something, which we end up here with a value of 3. Okay, so this is how I would say the raw term frequency inverse document frequencies are calculated. And the default setting, so here, by the way, also here you can see if you're scoring this or if you're looking at the notebook for yourself later on, this is how we would manually do this, but this is just what I've been talking right now. And now here is something about normalization. So let's take a look, because if you don't set norm to none here, then you get numbers which are not, you don't really see how is it possible that you have a inverse document frequency weighting of 1.9 and you multiply this with that value and still you end up with a value below 1 here, okay? So what is done here is a so-called L2 normalization. So that means, let's go back here for one time. So if this is a vector, okay, and here I'm kind of assuming you have this background knowledge what a vector is. Very simply speaking, a vector is just a certain number of numerical elements that describe it here. I mean, this is really, sorry to everyone who is more formal in terms of mathematical definitions. Obviously, a vector is a very general and interesting concept in the area of math, but for us at the moment here in that application, it is just a sequence of numbers that do characterize, in our case, the documents in a certain way. And you can normalize a vector by dividing it by, for instance, its L2 norm. And the L2 norm is here the length of the vector. So it is basically the sum of all the elements to the power of 2 and then taking the square root of it. And if you divide by this length of the vector, then you get the normalized version, because the length of this normalized vector will always be equal to 1. Okay, so, and this is does also make sense because in the textual analysis area, we often, for instance, want to calculate what is called later a cosine similarity. We do not talk about this at the moment, which, for instance, quantifies to us how similar two sentences are to each other. And if you want to calculate this, it is very helpful if you have vectors normalized. And also, by the way, normalization kind of restricts the number to be in a smaller numerical range, which is also often very helpful when using this numerical representation for machine learning algorithms, because many machine learning algorithms need data to be standardized in a certain way, and here you also would have this. Okay, so you basically, even if it is of direct use, it doesn't do any harm, and it may simplify things in terms of having a smaller numerical range, which is often also helpful for other things that are going to be done with that, right? So I think these are one of the few things that are very interesting just in technically how you derive those numerical representations. By the way, still we're taking only a look here at counting words, or counting how many times does a term occur in every document. And one time it's the raw counts, and the next time it is weighted in some way that may make sense in especially giving high weights to terms that may be of great relevance in differentiating those documents here. Okay, so this is, by the way, how you would call it, and even if you let this out, this is the default setting here. All right, and so if we have this normalization here, I included the example here, which I've been talking before. So for instance, if you now create the dot product between the two matrices here, what you would get, even though without talking about it here, you would get the cosine similarities. And here, for instance, this would tell us that for the first sentence, it is the third sentence which are most similar to each other. And if you take a look at those sentences by yourself, I mean, we can go here to the beginning. It is at least sentences where we have, for instance, company and something with a production here. Okay, so production and the company. So this kind of makes sense. Okay. All right. I would say at this point, there's a good point to pause and stop this video. And then in the next videos, we're going to take a look at the overall process. Now that you have your numerical representation, what can you do with it? All right, so see you in the next video, hopefully. And yeah, take care.